So this is a rule. A string in C has to be terminated by a null character, and that's why we need one extra space to store this null character. Let us try to see some running code that will help us understand this concept better. What I have done here is I have taken a character array of size 4 and I have filled in the characters, but I have not used any space to null terminate it. And then I am using the printf function. This percentile s here tells that I want to print a string, and then I'm passing this array C. Let us run this program and see what happens. As we can see, there are these bunch of characters that are getting printed after John. This is happening because we have broken the assumption for the printf function that my string, that our string will be null terminated. So that's why this undefined behavior is coming. If we change the size of the character array to 5 and put a null termination, something like this, at 4th index, and then things will be fine. Now even if we change the size of the array to 20, printf function will print till it finds a null character. So it only prints the first 4 characters in the array. And it's not just the print function, there are a bunch of functions. We have this library string.h that gives us a bunch of functions for string manipulation. So all these functions assume that the string will be null terminated. So this is one contract that we have to follow. Let's say we want to use one function strlen, string length, to find out the length of the string. I'll print something like this. Let's run this and see. As you can see, the output is length is equal to 4, even though the array is of size 20. So string length function also counts till it sees a null character. In our program, instead of writing these characters individually at these positions, we could have used string literals. String literals are a group of characters within double quotation marks. So we could have written something like this, and this would have initialized C as this string, and the null termination for a string literal is implicit. It is always stored with a null termination in memory. Remember, when we declare and initialize a character array like this has to happen in one line. We cannot do something like we declare in one line and then we go on and modify this in the next line. This will be invalid. We could also avoid writing this size here, and this would have been fine. In this case, the size of C will be 5 units, 5 bytes, where 1 byte stores 1 character. So it would be just enough to store the string John. So if we try to print the size in bytes of C using this size of function, then size in bytes is 5, 1 character is stored in 1 byte. So space has been allocated for 5 characters, but the length is 4 because the null character does not count in the length. If we write something like C4 is equal to this particular string literal with 4 characters, this will give us compilation error because the compiler will force this particular array to be of minimum size 5. There is one more syntax of initialization. We can put all these characters as a comma separated list within these braces, but in this case the null termination will not be implicit. We will have to do it explicitly, and the size of the array has to be greater than or equal to the number of characters here, so it should be greater than or equal to 5. Okay, so these are some of the ways to initialize character array. The next thing that we need to understand is arrays and pointers are different types that are used in similar manner. Now what does it really mean? Let's say we declare a character array C1 of size 6 and initialize it with this string literal, and let's say this is how it gets stored in the memory. Array is stored in one contiguous block of memory. So let's say the first character is at address 200, one character is of size 1 byte, so the next character will be at address 201, and the next will be at 202, and so on. Now C1 is the variable name for this whole array. Now what I'll do is I'll declare a variable which is a pointer to character. Let's name this C2. So let's say we get this variable C2 somewhere in the memory. A pointer variable in a typical architecture is stored in 4 bytes. So this variable will also have some address. Let's say this variable is at address 400. I'm just picking up these numbers for example's sake. Now what we can do is we can write a statement like this: C2 is equal to C1. Now even though C1 is a character array is a variable name for character array, and C2 is a variable which is pointer to character, this particular expression is valid. Just using the name of the array actually returns the address of the first element in the array. So what this statement will do is it will fill in the address 200 in C2. So C2 now points to the first element in the array. Now we can use this variable C2, which is a character pointer, just like C1 to read and write into the array. So if I write something like print C2I, let's say we want to print C2 1, then the output will be L, and we can even modify the array. Let's say we want to modify the character at 0th index to A, so the string will be modified and will become this. When we write C2I for any position I, it is nothing but asterisk C2 plus I. So C2 is the base address, C2 plus I will take you to the address of the ith element. So in this case, let's say C2 plus 2 will be 202, and if we put this asterisk operator, we are basically dereferencing and finding out the value. So these two syntaxes are alternate syntaxes, and even if it is an array name, we can write these two as substitutes for each other. So this was all the similarity in how we actually use arrays and pointers to read and write. Let us now look at the differences. We cannot modify an array with a statement like this. C2 equals C1 is valid, but C1 equals C2 is not valid. It does not make sense. This will give you compilation error. We cannot even say C1 is equal to C1 plus 1. We cannot increment or decrement this variable C1. We can do it for C2, which is a pointer variable. We can say C2 plus plus, so C2 now points to the next element. And with this statement here, all that will happen is C2 will become 201, so instead of pointing here, it's now pointing to this particular element E. To traverse an array, we run a loop and we use a local variable, let's say I, and increment it in the loop. If we have a pointer variable, we can just keep on incrementing the pointer and we can traverse the list, we can traverse the array. We will keep doing this C2 plus plus. So we must understand where we have an array and where we have a pointer and what we can do with which one. Now the next thing that we need to understand is that arrays are always passed to functions by reference. When we pass arrays to functions, we only pass the base address of the array in a pointer variable, and we do not pass a whole copy of the array. The compiler does not let you do that. We have talked about this in detail in our previous lesson. Arrays as function arguments. Let us go through some code and try to understand this better. In my code, I have declared a character array size 20, and I have stored a string of length 5 in this character array. The null termination is implicit if we are using string literal. Now I want to print this string, but I do not want to use the library function printf. I want to write my own function print. I want to pass this array to the function, and this function should print the string part in a character array. The argument to the function, we have talked about this earlier, can be something like this to say that we are receiving an array here, but the compiler actually interprets this as this. So the compiler forces that only the address of the character array or the address of any array be received as argument to the function, because arrays are large in size, so it is inefficient to create a copy of the same array for each function. Okay, so let's write the logic now. Now this print function does not have any idea that this particular array is of size 20. It only knows the base address. So what we can do is we can have a variable I, initialize it to 0, and we can say something like this: while ci is not equal to null character, we can print the character ci, and then we will increment I, and when we find a null character, we can come out of this loop and print an end of line. Once again, this print function does not know that this character array is of size 20, it only knows the base address. And that's why in the printf function, when we were not null terminating an array, we were printing all the garbage value even after the array was finished, because until we get a null character, we do not know where to stop, and we keep on going into my code here I'm using %c here to say that we want to print character, and ci we can also write asterisk c plus I as substitute for ci, and that will also mean the same. Sometimes you'll see this kind of syntax. As we talked earlier, both of these syntax asterisk c plus I and ci are valid, they are the same. There is one more thing in our code that we may do. We may not choose to have this particular variable I. We could simply say that while asterisk c is not equal to null, print asterisk c and then increment c itself. And this code will also work. Why this code will work, I'll leave it as an exercise for you to think. In the coming lessons, we will implement more functions for string manipulation. This is it for now. Thanks for watching. In part 1 of our lesson on character arrays and pointers, we saw how we can store strings in character arrays, and we also saw how we can work with character arrays using pointers in some of the basic scenarios. Whenever we are working with pointers, it's really important that we visualize how things are happening in the memory. So the first thing that we will do in this lesson is we will simulate the program that we had written in the previous lesson to print the characters of a string and see what goes where in the memory. And we will also look into the concept of string constants and constant pointers. So this is where we had left in our previous lesson. We have written a function print to print the characters in a string. In the main method we have a character array of size 20, but we have stored a string of length 5 in it. We have used a string read12, so null termination is implicit. We have talked about this earlier. So let us step through this code and see how it is working. Once again I have drawn this familiar diagram. The memory that is allocated for execution of a program is typically divided into these 4 parts, these 4 sections. One part of the memory stores the instructions in the program. We call that the code segment or the text segment. One section stores the global variables, and stack is where all the information regarding function call execution and all the local variables go. Whenever we are writing a program, whenever we are executing a program, we should always visualize what variable goes where, or what data goes where, and what is the scope of that variable or data. Okay, so let us run through this code and see what is happening in the memory. When this program will start executing, first the main function will be invoked. Whenever a function is called, some amount of memory from the stack is allocated for the execution of that function. It's called the stack frame of that function. So let us say this stack frame from address 100 to 150 is allocated for the main function. Stack is one contiguous block of memory. So let us say in the stack the memory increases from bottom to top. All the local variables of a function go into the stack frame of the function. So when we declare a character array, 20 bytes from this stack frame will be allocated for this particular character array. Let's say they are allocated from address 100 to 120. Each character is stored in 1 byte, so we need 20 bytes for character array of size 20. Apart from local variables, there may be some more information in stack frame, so that's why we have some more space. And now the control of the program goes to this thing, print C. As soon as we make a call to another function from a function, the execution of that particular function is paused at that particular line, and the machine goes on to execute the called function. The called function is allocated stack frame on top of the calling function, so print will be allocated a stack frame on top of main function. Whatever function is at the top of this stack and at any point is executing, main will wait for this function to finish. Let's say this particular stack frame is from 150 to 170. Main is paused and print is executing right now. Now print will also have a local variable C, but this will be a pointer variable. A pointer variable takes 4 bytes of memory in a typical architecture, so this will be taking 4 bytes. So let's say starting address 154 in this stack frame, we have 4 bytes for this particular character pointer. So this C in main is actually not the same C in print. The C in main and the C in print are different. They have different scopes. We could have named this particular variable A or PTR or whatever. But all that happens when we make this particular call to print and pass this C here is that the address 100, which is the base address of the array, is passed to the print function, and the print function keeps it, stores it in a pointer variable. Sometimes it may confuse us when we are using the same local variable name in the calling function and the same argument name in the called function, but we must always understand that they are different. Okay, to run through this code further, I'll clear some space here now. I'll draw this array C outside the stack here. We have an array of size 20, but we are only showing the first 6 positions in the array from address 100 to 105, and that's why it is extending towards the right. The 6th character is a null character, and the first 5 characters are the characters of word hello. Now we have this another guy, which is C of print, which is a character pointer at address 154 that stores address 100, so it points to the first element of the array. Now let's come back to our program execution. Let's say we are here initially. I'll mark the statement that is executing by this green arrow. Let's name these two guys. This guy is C, but this guy is an array local to main, and this is also C, but it is a character pointer local to print. Okay, so now here what we're saying is, while asterisk C is not equal to the null character, when we put this asterisk operator in front of a pointer variable, we are looking at the value at that particular address. So at this stage, when C is pointing to the base address, asterisk C is H, so this condition is not true. We will go to this line printf, that will simply print asterisk C, which is H. Let's write down the output here. So we have printed H so far, and then we say C++. If we understand pointer arithmetic from our previous lessons, incrementing a pointer by 1 unit increments the address by size of the data type that the pointer points to. C here is a pointer to character data type, and character data type is 1 byte. So C plus 1, C++ is saying C is equal to C plus 1, so C now becomes 101. So now C points to the second character in the array. And once again we come to verifying this condition in the while loop. Asterisk C is E here, it's not null. Once again we will go inside the loop and print E, and we will keep on going like this till the address in this pointer variable reaches 105. Now here the value at this particular address is null character, so the loop will not execute. We will come to this statement to print an end of line, and the execution of print function will finish. So this particular stack frame for print will be cleared from the stack, will be deallocated, and now main will resume and finish. So with pointers we should always know what's going where in the memory. Okay, so let us now modify this particular code to learn some more concepts. What I'm going to do in my code is, instead of creating a character array of size 20, I'll create a character pointer named C and equate it against a string literal in a statement like this. And if you run this program, the output will be the same. What really happens is, if you use the string literal in initialization statement of an array, something like this, and then the string gets stored in the space that is allocated to the array. So in this case it will go into the stack in this character array of size 20. But if you use the string literal elsewhere in a statement like this, or maybe when we do something like passing a string literal to a function, then in these cases the string gets stored as a constant during the compile time. Most probably it will be stored in the text segment of the application memory, and it cannot be modified. So if you write a statement like this, let's say you want to change the first character of this constant string to A, running this program will give you an error, will cause a crash. Okay, coming back to having a character array. Now if we have a character array and we are passing the address of the array to a function, that function receives it in a character pointer. Now using this pointer we can modify the data in this particular array. So if I say something like this, we first change the first character to A, and then we are printing characters, and then as you can see, it is possible to do so. Now sometimes we may want a function just to read a string and not write anything. To force this kind of behavior, we can change our argument to const character pointer. And now if we run this code will give us compilation error. We can read whatever is there in the array that is passed, but we cannot write to any of the positions. This code will work fine. Pointers are really tricky, and even the most experienced programmers write buggy code when they are using pointers. I recommend that you get your hands dirty by writing some code yourself. That's the best way to learn. So this is it for this lesson. Thanks for watching. In this lesson, we are going to talk about pointers and multi-dimensional arrays. As we have seen in our previous lessons, the concepts of pointers and arrays go together. We have already talked about pointers in context of one-dimensional arrays, how we can work with one-dimensional arrays using pointers. Now let's see how we can work with a two-dimensional array or a three-dimensional array or a multi-dimensional array in general using pointers. To understand this concept, once again, we first need to understand how multi-dimensional arrays are organized in computer's memory. Let's first go back to the organization of one-dimensional arrays in memory. When we declare a one-dimensional array, something like this, let's say we are declaring an integer array A of 5 elements, then basically what we are doing is we are creating 5 different integer variables that we can name A0, A1, A2, A3 and A4 as one contiguous block of memory. What I'm showing here is a section of computer's memory. Array A, let's say, is stored in this section of memory, and the starting address of A is 200. As we know, each byte in a computer's memory has an address, and if we assume that an integer is stored in 4 bytes, which is what it takes in a typical compiler, then the block of 4 bytes starting address 200 will be A0, as I'm showing here. Block of 4 bytes starting address 204 will be A1. Next block of 4 bytes starting address 208 will be A2, and so on. I'll fill in some values here. We had seen this earlier also in our previous lessons. If we write a statement